This is part 4 of the Module 10 lecture. In this part, we're going to talk about the test of independence or homogeneity, which is the second application of a chi-square test. And this is covered in section 11.3 of your textbook. Okay, the test of homogeneity and the test of independence, that's a method of analyzing contingency tables. And if you might remember that we talked about these tables in module 4 when we talk about probability. A contingency table, or a two-way classification, summarizes the frequencies of two attributes, what we call the column attribute and the row attribute. We also call this the R by C table. And the R by C table is a contingency table with R columns and C columns. Also, we use the I, J indexes to designate a row number and a column number. For example, this table is a 3 by 4 table. 3 because it has 3 rows. So the row attribute has 3 categories, A, B, and C. And 4 because the column attribute has 4 categories. Also, for example, this is the cell 2, 3, where 2 is the designation of the row number. So 2, this is the second row. And 3 is the designation of the column number. So this is the third column. So this is the cell 2, 3, or the observation or the frequency 2, 3. You will see how these indices are useful in subsequent slides. All right, contingency tables, you might remember from module 4 that each cell frequency is the joint frequency of a row attribute and a column attribute. Also, the row marginal frequencies, or the row totals, this is the result of adding all the frequencies for a particular row across columns. So for example, this row total of 74 results from adding 20 plus 25 plus 10 plus 19. In the same way, 102 is obtained by summing the 4 frequencies across the columns for row B, and for row C, or the third row, again, if you add these frequencies across columns, then you find the row total of 67. If you add the row totals or the column of the row marginal frequencies, then you get the total of all observations. And again, if you add the frequencies for a particular column across all rows, like 20 plus 23 plus 17, that gives you 60. The same way for the second column, you add the frequencies across rows for this particular column and you get 55. The same for column 3, you add these 3 quantities and you get 60, and for column 4, you add these 3 quantities and you get 68. If you sum the column marginal frequencies, or column totals, you get the total number of observations. So this is the structure of a contingency table. All right, so we're going to look at these tables in 2 possible ways: as a test of dependency between the column variable and the row variable, or as a homogeneity of the columns across the row categories. All right, again, because we're performing a test of hypothesis, we will follow the 5-step process. And I'm showing you this because this guides the discussion that follows. So first we're going to talk about how we state the hypothesis for each of these tests. Then we talk about what distribution to use, how to calculate the test statistic, how using the p-value or the critical value we make a decision about the null hypothesis. And the difference between the test of independence and the test of homogeneity is in how we state the null hypothesis and alternative hypothesis, and how we interpret the decision of rejecting or not rejecting the null hypothesis. Otherwise, the procedure to perform the tests are completely identical. All right, so let's look at the hypothesis for the test of independence. So in the test of independence, the objective is to determine if the discrete column and the row attribute are dependent. And so the way we state the null hypothesis, we said the row and column attributes are independent. And the alternative hypothesis is that the row and column attributes are dependent, or we typically say they're not independent. And this test of independence is always a right-tailed test. All right, so in independence, remember, we're trying to determine if there is a dependency between the row attribute and the column attribute. And here is an example. And this example is the same from the textbook. When I provide an example of how to perform a hypothesis test, I will use a different example, but you can see the solution of this example on your textbook. All right, in this case, in this example, it says violence and lack of discipline have become major problems in schools in the United States. So a random sample of 300 adults was selected. These adults were asked if they favor giving more freedom to school teachers to punish students for violence and lack of discipline. And the response of these adults are shown in this contingency table. So in here, we would like to see if there is a dependency between gender and the opinion of giving more freedom to teachers to punish students for disciplinary issues or violence. All right, and in this particular problem, we would like to determine if these two attributes, gender and opinion, are dependent, and we use a significance level of 1%. Again, I'm not going to solve this problem here on the slides. You can see the solution on the textbook, but I'm using it as an example to illustrate a test for independence. All right, a test for homogeneity, we look at this a similar contingency table, but now we have different information in the row and column categories. So in here, we would like to compare the proportions of elements with certain attributes of two or more populations and see if these proportions of these attributes are the same across the different populations. In other words, we say that they are homogeneous. So the hypothesis in a test of homogeneity are that the proportions within populations are homogeneous, versus the alternative hypothesis, the proportions with populations within populations are not homogeneous. And as in the test for independence, the test for homogeneity is always a right-tailed test. All right, so here's an example of a test of homogeneity. So in this case, a researcher is interested in comparing the income distributions for households in California and Wisconsin. And a survey produced the following results. So in this case, we have the attribute income, high, medium, and low, and we would like to see if the distribution of these levels of income is equivalent in California as it is in Wisconsin. In other words, we're looking to see if the proportions who have income are equivalent in California and Wisconsin, and to see if the frequency of the medium incomes in California and Wisconsin are similar, or if the proportions of the low income in California and Wisconsin are the same. So again, in this particular case, we want to use a 2.5% significance level, and we want to test the null hypothesis that the distribution of household incomes levels is similar for the two states. So how do I distinguish between a test of independence and a test of homogeneity? It comes from the context of the question. So again, if in the exam, I'll be very specific and very deliberate in telling you what situation we have. But in practice, nobody tells you that this is a test of independence or a test of homogeneity. You deduct that from the problem itself. So in here, for homogeneity, we're looking at a series of categories, and we want to see if they're homogeneous among two or more populations. All right. Once you make the distinction between how to state the hypothesis because you have a test of independence or a test of homogeneity, then what comes next is the same for both tests. So the distribution to use is a chi-square, as you would suspect. And the degrees of freedom now are calculated as the number of rows minus 1 times the number of columns minus 1. And as long as both classification variables are discrete and the expected count in each cell is at least 5, then we are justified in using the chi-square distribution. And the expected counts, I'm referring to the expected counts for each of these cells. So if the expected count is at least 5, then we're justified in use the chi-square distribution. All right, let's see how we do this. All right, the test statistic, the test for either high independence or homogeneity, we use this chi-square statistic where we sum across rows and across columns the observed frequency minus the expected frequency. We square that and divide that by the expected frequency of a particular cell. And as I mentioned earlier, the I in subindex designates the row number and the J subindex designates the column number. So the OIJ is the observed frequency for the cell I, j. Again, I and j will be numbers. And the expected count for the cell ij is given by this equation. So we're going to multiply the row I total times the column j total and divide that by the sample size. So the total number of observations in the contingency table. So that's how we're going to calculate the expected values. And again, I'll show you an example of how to do this. So once we calculate the expected value for every cell and the observed values for each cell are obtained from the experiment, so then we will know all this information and we'll have then used to carry out these calculations for every cell. All right, so that's the test statistic. And again, this will become clear once we work through some examples, or at least that's my hope. All right, once you calculate the test statistic, then if you decide to follow the critical value approach to make a decision about the null hypothesis, either of a test of independence or a test of homogeneity, then because they are always a right tail test, then you know that the rejection region is on the right tail of the chi-square distribution. So to find the critical value that separates the rejection region from the non-rejection region, we use table 6, the chi-square table. And we use the level of significance together with the degrees of freedom to find this value. Once you find the critical value, then if the computed value of the test statistic lies in the rejection region, well, we will reject the null hypothesis. So the same rule as before. If you decide to use the p-value approach, again, we have a right-tail test, and the p-value is the probability to the right of the value that we calculated for the test statistic. Like that's what is shown in this figure. Again, from table 6, all you can find are rough bounds for the p-value. And you do that by looking at the row of the degrees of freedom of this distribution and finding within which values the chi-square observed is. And that's the value of the test statistic that we calculated. Now, if you want to find the exact p-value, you can use this formula in Excel and you will find the exact p-value. And the rule to reject the null hypothesis is the same as before. If the p-value is smaller than alpha, we reject the null hypothesis. All right, so in the next recording, we'll talk about an example of test of independence, and then in the next recording, we'll look at a test of homogeneity.